Okay folks, I want to talk to you about the reduction formulas and putting angles on the Cartesian plane. If we look at our Cartesian plane has our y and our x-axis usually. Now if I form an angle, remember an angle is formed by an initial ray and a terminal ray. So this will be the terminal arm of a point P, and let's just say that's the coordinate pair x and y. Okay, the angle that is formed is the positive angle over here. It's measured anti-clockwise. Now if I take this point P and I reflect it in my vertical axis, then I will end up with something that more or less lies over here. Okay, so I'm taking point P and I'm reflecting it in the vertical axis. So point P will now lie at this point, which is a minus x and still the same positive y value. So if I draw in my terminal arm over here, you can see that we were forming two angles that are actually equal to one another if I look at it from this perspective, from the horizontal. Okay, so if I now assign a value to this angle, I say that angle is 30. If I want to get to the angle that lies over here, which is also going to be a 30 degrees, that angle I get to by saying I start at the terminal ray and my terminal arm finishes in that position. So if we look at this, this is a straight angle. This angle over there will actually measure 150 degrees. But now, if I talk about the 150 degrees, or whether I talk about the 30 degrees that it is away from this horizontal over here, the terminal ray is still in the same position. The coordinates have just reflected in the y-axis. Okay, so folks, that's very important to realize. So if I now extend this point, or I reflect this point in my x-axis, I'm going to end up down here with point P. Now if I join there, that point or that line is indeed a straight line. So here I get minus x, the x values are shared, and minus y, which now lies in that position. Now we've just seen now that because of our reflection, it's literally, we can think of it as that triangle reflected in the x-axis. So this angle will again be 30 degrees. But because I started measuring the angle here, I'm going to try and draw the circle as nicely as I can. I'm actually talking about 210 degrees. And 210 degrees is still related to 30 degrees. It is 30 degrees away from this horizontal. Okay, we'll assign the angle values in a moment. If I look at the last reflection, and that will be the reflection of point P, in this x-axis, I reflect it through the x-axis. It is now in this position, or I can think of it as a reflection of this point in the y-axis. But now again, if I join that line from here to actually form my angle, sorry, it looks a bit wobbly, but then I can see again, it's a situation where I've had this triangle over here reflected in the x-axis, so my little angle 30 over here is again appearing. But remember, it is starting here, I go 180, 270, and I end at that point there. So that blue angle will be 330 degrees. Now that is exactly what we're going to do if we start talking about horizontal reduction formulae. Okay, the point P over here will have the same x value and the y value will be a negative. Okay, so let's see how this now plays out. If I now decide to say, fine, let us talk about all these angles in terms of this horizontal line, and I'm going to draw this line in red so that it stands out. So where I was talking about an X and a Y axis, I'm now going to be talking about the 4 quadrants that are created on the Cartesian plane. And because I'm forming angles, my 0 angle would lie over there. I go through to this vertical line, I would have rotated my terminal arm, my initial ray is over here, my terminal ray would then be on the vertical at 90. Rotated another 90 degrees and I'm back on the horizontal line. So from there to there I would have measured 180 degrees. Add another 90 and I'm at 270 degrees. Go through another 90 and I've done a full revolution at 360. Okay, so if I now assign values or numbers to these quadrants, then I will have something more to talk about. So I'm going to do that in highlighter so that we can remind ourselves that our Cartesian plane will be divided into 4 quadrants. So this will be quadrant 1, this here will be quadrant 2, this is going to be quadrant 3, and we're going to talk about that as quadrant 4. I see it doesn't show so nicely, so let me just write in the quadrant numbers. Okay, so if I'm in quadrant 1, folks, you will agree with me if I replicate my Cartesian plane over here in terms of degrees, 0, 90, 180 degrees, and 270 degrees, that in my first quadrant, all my angles will be smaller or than equal to 90 if it's on the line, but I want to only talk about the quadrant itself. Okay, so in that quadrant, all angles are smaller than 90. If I go into my second quadrant, now remember my second quadrant angle was this 150. Started on the initial ray and it went 150 degrees into the second quadrant. It was 30 degrees away from this horizontal. So if I want to end up in with the same terminal position over there, I can go and say the following. I can start at my 0 degree, my initial ray. I can go to 180 and I bounce back the 30 degrees. Then I am again at the same terminal position. So whether I will be talking about bouncing back 30 or just moving 150 to get to that ray, that is the same position for the terminal ray. So if I want to work in the second quadrant, I can go to the horizontal line and bounce back. I go to the horizontal and I bounce back however many degrees I was working with to get to the same terminal position. Now the same in my third quadrant. If I want to talk about my third quadrant, my angle was the pink angle, 210. I can go the same route. I go to my 180, but then to get to this terminal arm, I bounce more and I bounce on however many degrees I was working with over here. So I can say that this will be 180 plus a particular value for the angle that I'm considering. And guys, the same happens in the fourth quadrant, but the fourth quadrant is a special case. If I want to focus on quadrant 4, I can go one of 2 ways. I can go, and remember the angle that I'm going to be focusing on is this little angle over here. So I can go all the way around, I can go 360 degrees, and from the 360 I bounce back the amount of degrees that I'm considering, which in this case is 30, but I'm generalizing, so I'm going to call it a theta. So I can say I go a full revolution and I bounce back the amount of degrees, the theta degrees that I need to come back from the horizontal. Now there's 2 things I can do there. I can either say I go the full revolution and come back, Or I can just see it that from this horizontal I moved theta degrees in a clockwise direction. Hence, I am sitting with my negative angle. Okay, so I can say it's 360 minus theta, meaning I go full, come back, or I can just bounce down from my horizontal. Okay, now there's a lot of different things to remember here. The first thing is that for my angles that change sign. So if I'm talking about a negative theta, just think for yourself. You can't say I'm walking minus 50 meters. And for the same reason, there cannot be negative angles. I cannot say an angle measures minus 10 degrees and actually mean that it's negative. This negative in front here indicates the direction in which you measured your angle. The angle direction here is a clockwise direction. Okay, if the angle is positive here, there's a plus in front of here, invisible, so the direction will be anti-clockwise. So I measure in that direction. Clockwise direction, I measure in this direction, away from the initial ray, or then the horizontal in my diagram. Now folks, this links up beautifully with what you have learned in grade 10 about your function. If we draw our, let's just look at one function, let's look at the sine function for now. If I draw my sine function, we know sine maximizes at 1, minimizes at minus 1. It reaches a 0 at 180 and at 360, 90 and 270. It has maxima and minima. So if I quickly draw in my 4 quadrants or my 90 degree multiples, I am going to go up, I maximize, I turn back to 180, I reach a minimum at minus 1, and then I turn back to 360. Now look at how beautiful this is, guys. If I now indicate my quadrant lines, there's from 0 to 90. This is quadrant 1. From 90 to 180, on this diagram at the top, it is quadrant 2. Then from 180 to 270, we have quadrant 3, and then in quadrant 4, we have from 270 to 360. Now just look at this. If I choose, let's say, the sine of 30 degrees. The sine of 30 degrees lies at a half. So this here will be 30 degrees. Now that value will repeat itself over here. The value of a half repeats itself again over there. Okay, how far is that? Well, that there comes from the 180 degrees, I move 30 back, and I'm at 150. So again, to get to 150 on the rotation scale, I go to 180 and I bounce back 30 degrees. Hence, I go 180, come back 30. The value repeats itself. If I'm looking at where sine is minus a half, okay, minus a half lies over here, and again I am at a point where I am 30 degrees further than the 180 line to get to 210, which lies over there. So 210 was 180 plus my little bit. And then to get to the last point where sine will be minus a half, it is 30 degrees back from the 360 line. And that's exactly how the rotated angles work. And that's exactly what we've got here in terms of the reduction. So we give that a name. We call this the horizontal reduction formulae. Okay, because we are bouncing back from the horizontal, whether we bounce on or whether we bounce back. Bounce on, bounce back. Okay, that brings me back to one more angle that I need to fill in here for you guys. Now let's look at this. This angle over here, if you close your eyes and I tell you open your eyes, you wouldn't know, did I just do that or did I go around and bounce on? You won't know that. Okay, so, and that's the beauty of what reduction formula does for you. You don't know what happened to get there, but you can make a clear guess and you can generalize that guess. You can say to yourself, fine, you could have just gone 30 degrees across, you could have gone 3 revolutions and then stopped there, we won't know. Therefore, I want to add another reduction rule in here, and that is the reduction rule that says 360 plus a theta, because the terminal position will be in exactly the same place. I start with my initial, I go around, and I can bounce on the theta degrees. The terminal position is exactly the same. Okay, now let us look at what the sine and the quadrants, then what we can say about them. If I go back and I draw my Cartesian plane over here, from 0 to 90, the y values of sine are positive. So here the sine of any angle is positive. From 90 to 180, the sine of any angle will still be positive because the graph lies above the x-axis. Then if we go from 180 to 270, we see the sine curve goes negative all of a sudden. So the sine of theta from 180 to 270 is negative on the curve of sine. And again from 270 to 360, it is still negative. So we're back at 360. So we can say that in the first 2 quadrants the sine function is positive. In the next 2 quadrants the sine function will be negative. Now let's look at the same for cosine. You can remind yourself the cosine curve starts at 0, goes to 90, goes to 180 minus 1, back to 270 and then to 360. This is 90 degrees. That there's 180 degrees. This here is 270, and there we have our 360 degrees. Sine and cosine both optimize at 1 and minus 1. Okay, now let's see, between 0 and 90, look at that, cosine is positive, so there's my quadrant 1. Here's my quadrant 2. There lies my quadrant 3. That's the school bell. There goes my quadrant 4. Okay, so in quadrant 1, cosine of theta was also positive. But in quadrant 2, which goes from 90 to 180, cosine of theta is all of a sudden negative. And then it remains negative from 180 to 270. So here cos of theta is still negative, and here in the 4th quadrant, the cosine of theta all of a sudden becomes positive. Okay, and the last function that we need to look at is the tan function that you learned about in grade 10. Now this was a special function. At 90, it had an asymptote. Okay, there's quadrant 1. At quadrant 2, which lies here, so this is 90, this would be 180. Then there was another asymptote at 270. And then we had the final portion of this graph from 270 to 360. So tan started here and went to its asymptote. So in the first quadrant, the tan of theta was also positive. But then also, like cosine, in the second quadrant, tan was negative. So here the tan of theta became negative. Okay, in the third quadrant it continued towards the asymptote, quadrant 3. Tan again was positive, and notice it's the only function that's positive in quadrant 3, and then in quadrant 4 it became negative again. So we have our 4 quadrants: quadrant 1, quadrant 2, quadrant 3, quadrant 4. And to remember all of this is a lot of work. So we're deciding that we're only going to remember where things are positive. Now if you look in the first quadrant, sine, cos and tan are positive. In the second quadrant, sine is positive. Anything else that's not positive there is negative. In the third quadrant, tan is positive by itself. And in the fourth quadrant, cosine will be positive. And folks, that is turned into the rule that we refer to as the cast rule. In other words, and it's based on the first letters of the ratios. So in the fourth quadrant, cosine is positive. In the first quadrant, all of the ratios are positive. In the second quadrant, sine is positive. And in the third quadrant, tan is positive. Sine and cos will therefore be negative. So remember, starting from your fourth quadrant, the cast diagram tells you where things are positive. C stands for cos, A stands for all, S stands for sine, and T then stands for the tangent. Now just a reminder again, we started and we said, let's look at what happens if we reflect our point, our terminal point on our terminal arm in the y-axis, in the x-axis, in the y-axis. It is the same as reflecting this triangle over here, which, by the way, all these triangles are right-angled triangles because we drop the altitude from point B. So this will also be right-angled, that will be, and this will be as well. It's reflected in the vertical line. We can think of it as a bounce off or a bounce on if it's in the third quadrant, and in the fourth quadrant we can bounce down first of all, which means we're working with the negative angle. But the beauty of that was that this negative theta there was the same as saying it's 360 bouncing back a theta. And the final additional reduction formula I introduced you to is again going to the first quadrant and saying, you know what, there's an option. We could have started, gone a revolution and bounced on a theta degrees. Hence here our horizontal reduction formulae. Okay, and then we said let's look at how this angles of rotation now plays out in the functions that we've become familiar with in grade 10. We looked at the mother curves. This was y is the sine of theta. This was y is equal to the cosine of theta. And this was the mother curve for the tan of theta. In each of these quadrants, we checked where are they positive, where are they negative. Okay, and we decided we're going to remember or remind ourselves that we need to know where they are positive only. The third thing that was important here is to show you how the reduction formulae actually plays out in the graph. I can go 30 degrees in rotation, then I'm there on my graph. Then I go to 150, which lies here, which is 30 degrees away from the horizontal, here the vertical line 180, here the horizontal. So we go bounce back 30, we are at 150. We bounce 30 on, we're at 210. Okay, and then we go all the way around and we bounce 30 back, we are here at 330 degrees. So your horizontal reduction formulas come from the beautiful symmetry in the trig functions, the mother curves, or it comes from the symmetry that's created if you take a initial ray and you create a terminal ray which forms an angle with the horizontal, and you start reflecting that terminal ray in the different x and y axes. In other words, the vertical and the horizontals. Okay, in the next video clip, I'm going to look at bouncing off from the vertical. I hope that made sense to you guys.